Hi again, you're watching my YouTube channel Concept Tech 2018 and I'm Sunanda Manke. This is part 1 of the video series of power amplifiers. In this series, we'll discuss each and every aspect of power amplifiers. After watching this series, you will learn the know-how of power amplifier, class A, B, C, D power amplifiers, numericals based on them and their comparison as well. In this first part, basics of power amplifiers, its types and related parameters will be covered. Coming to the definition of power amplifiers give high output power. Figure shows a multi-stage audio amplifier in which microphone output is amplified and fed to the speakers. Multi-stage amplification is required to achieve high gain. In multi-stage amplifiers, initial and intermediate stages are small signal amplifiers or voltage amplifiers, whereas the final or the output stage drives the devices like CRT, transducer, servo motor, or in this case a loudspeaker. So a power amplifier is used as the last stage of amplification. It is a large signal amplifier, that is, it is capable of delivering large voltage and current swings, and appreciable amount of power is obtained at the output. The main features of a power amplifier or a large signal amplifier are its power efficiency, the maximum amount of power that the circuit is handling, and the impedance matching to the output device. Impedance matching is required to transfer maximum power to the load. As power amplifiers are large signal amplifiers, this slide shows the comparison between small and large signal amplifiers. In small signal amplifiers, the peak to peak swing in collector current is less than 10% of quiescent collector current, that is the operating point collector current. Whereas in large signal amplifiers, as you can see in the figure, the peak to peak signal covers most of the load line, that is, the swing is quite large. The output power in small signal amplifiers is in milliwatts or maximum up to 1 watts, whereas in large signal or power amplifiers it is in the range of tens of watts or even more. Small signal transistors are typically used at the front end of the system where the signal power is low, as shown previously in a multi-stage amplification. And the power transistors or power amplifiers are used near the end of the system because the signal power and current requirement is quite high. In small signal amplifiers, the transistor behaves linearly as the input signal variation is small. Linear behavior means dynamic characteristic curve is a straight line. What does that mean? That means the input-output signal relationship is linear, and in large signal amplifiers, input and output signal relationship becomes non-linear as the output signal amplitude or output signal swing is large. The output characteristic curves of a transistor, you must have seen the curves, they are neither equidistant nor they are straight lines. As the large signals pass through all these curves, the non-linear behavior of the transistor comes into picture. For small signals, this is not the case, so transistor behaves linearly. Now we will discuss the types of power amplifiers in this slide. Amplifiers are classified based on the location of the Q point or the operating point. In the first type of power amplifiers, it is class A amplifier. In this type, the Q point is located at the center of the active region, and this is done to make sure that the transistor remains in active region for complete input cycle. Thus the amplifier gives output for all values of the input signal, and we can say that the conduction angle of the transistor is 360 degrees. As shown in the figure, the collector current is obtained for complete 360 degree cycle. In class B amplifier, the Q point is located at cutoff. So in the positive cycle of the input signal, the transistor comes into active region and we get the output current for positive cycle. But in the negative cycle, transistor remains in cutoff region, so we do not get any output, and thus the conduction angle is 180 degrees. Next is class AB. As the name says, the class AB operates between class A and class B, and the Q point is located slightly above the cutoff, and that's the reason its operation is similar to class B operation, and conduction angle also is between 180 and 360 degrees. The output waveform is more or less similar to class B amplifier. In class C operation, operating point is located below cutoff, and so transistor conducts for small portions of the input cycle, and we obtain pulses of collector currents at the output as shown in the figure here. And conduction angle of course is less than 180 degrees. Class D is a special type of power amplifier. This amplifier works on digital signal or pulse signals. The input analog signal is first converted to digital signal, it is amplified and then converted back to analog signal. We will discuss all these amplifiers in detail in coming videos. Now we will discuss different parameters which are of importance in power amplifier. First and the most important parameter is the efficiency. It is also called collector circuit efficiency. This efficiency is defined as the ratio of AC output power to DC input power. Efficiency indicates how well DC power is converted to AC power. As we know that amplifiers give high AC output for low AC input. We know that energy can neither be created nor destroyed. Then from where did this transistor gets energy to increase the output level? Well, the transistor gets this energy from DC supply to boost the output signal, and thus more the efficiency, more is the DC power converted to AC output. Efficiency improves when we go from class A to class D amplifier. Another important parameter is the power dissipation. The DC power which is not used by the transistor or converted to AC is dissipated by the transistor. So, it is the difference between the DC input power and output power. Now, output power has two components, DC output power and AC output power. DC output power depends on the Q point or the operating point. If Q point is at the center of the active region, as the case is with class A amplifier, that means it has Q point voltage and current values. And this Q point voltage and current values gives us the DC output power. If Q point is at cutoff or below cutoff, as the case is with class B and class C amplifier, then its DC output power is 0, as the operating point or Q point collector current is 0. Harmonic distortion is another important parameter in power amplifiers. Harmonic distortion is the generation of new frequencies at the output. The new frequencies means the frequencies which are not applied at the input. These new frequencies are the harmonics of the input applied frequency. If the input frequency is say F, then we will have 2F, 3F, 4F and so on frequencies generated at the output. And these are called second, third or fourth harmonics of the input signal. For example, if we apply 1 kHz at the input, we will get amplified 1 kHz at the output, which is the desired value. Additionally, we get 2 kHz, 3 kHz, 4 kHz signals at the output, and these signals are termed as harmonic distortion. This type of distortion is present in large signal amplifiers or power amplifiers, and it is due to non-linear behavior of the transistor. As collector current no longer holds linear relationship with the base current, that is, IC is not equal to beta times IB, and because of this we get harmonic distortion at the output. We'll discuss this distortion in detail in video of class A amplifier. This is all about the basics of power amplifiers. Thank you for watching this video. Like, share and subscribe my channel Concept Tech 2018 for more such videos. Keep watching this series to get in-depth knowledge on power amplifiers. Bye for now.